Hi, my name is Sijia Zhu. I will introduce my team, Jianliao Yan, me, and Zimin Guo. We are do the whole project together. Today, Zimin Guo will responsible for introduction, data processing part, and the SVM model. Jianliao Yan will responsible for logic regression model and visualization. I will talk about the decision tree and the conclusion. Let's begin.
Zimin Guo. Today, we are going to introduce you to our final data mining project. Our project is about heart disease prediction. Our motivation behind this project. First, heart disease is the leading cause of death for both men and women. In the United States, more than half of the deaths due to heart disease in 2009 were in men. About 610,000 people die of heart disease in the United States every year. That's almost 1 in every 4 deaths. Every year, about 735,000 Americans have a heart attack. Of these, 525,000 are first heart attack, and 210,000 happen in people who have already had a heart attack before. We believe a reliable and thorough study in this field will have a greatly positive impact and help us find out more about this health crisis. Now, let's talk about the dataset. The original UCI dataset can be found here. This link is directing to the UCI machine learning repository, which is this website. This original dataset contains many attributes, more than we need, and is long been studied by many researchers and doctors. As I mentioned, there are 75 attributes in the original dataset, and we can find out that many of these attributes are not meaningful to us, nor useful for training machine learning models. A more refined dataset reduced the attribute space to a subset of 14, and this new dataset is available in Kaggle. As we can see, in Kaggle, this dataset is available for us to download. Let's move on to clean the data. In this dataset, a major issue is about quantifying categorical variables. In the original dataset, as shown in Kaggle, there are many features or columns, as we can see here, are categorical. For example, sex, CP, which is chest pain type, and many others are categorical. But in the dataset, they're represented by a number. Sex, for example, 1 stands for male and 0 stands for female. CP, another case, they have many numeric values from 0, 3, 2, and 1. This numeric value doesn't mean anything in numeric terms. Instead, they represent categorical sense. So, a CP, a change pain type, a total of 4 numeric values just represented different chest pain type. So, to solve this problem, we're going to use dummy variables. We create dummy variables to these features that are categorical and non-binary. The reason we are not dealing with binary data is that they already have a meaning behind them. And by creating dummy variables is to expand a single feature to many columns. Each column stands for a type. Let's look at the old example of chest pain type. We have 4 features. Then we have 4 features for this chest pain type instead of 1. So, for example, if the chest pain type is 2, in our new dataset, only the 2 chest pain type will be 1. All the other will be 0. so that the model can easily turn on and off for this type of column. We expect this method will greatly benefit the performance of one model we're going to use, which is logistic regression. But actually, we also hope there could be some performance improvement in the SVM we are going to use. We will talk more about that later. Also, we will compare and evaluate the processed data with unprocessed data to find out if there is a bump of a performance.
We have used and the visualization part in our project in this video. First, let's talk about logistic regression. Logistic regression is a machine learning classification algorithm that has widely used to predict the probability of a categorical dependent variable. In this case, is our target. There are some reasons why we use logistic regression. First, since our target is binary, which means the target only has two values, 0 and 1, then it actually makes logistic regression a good fit, since the logistic regression is suitable for prediction of binary target. On the other hand, we have found that logistic regression model can achieve very high effectiveness, accuracy, stability in our data set. Also, it's very easy to construct. Then there are some key steps for the constructing of logistic regression model. First, we've used a logistic regression package from sklearn linear model. Then we actually trained two models. The first model is trained by using original data that have not been pre-processed. Then we trained another model using pre-processed data. The process of pre-processing data is discussed by another teammate. Then we will compare the accuracy and the AUC of those two models to see whether pre-processing can affect the results of the model. Then, since parameters is very important to the success of constructing high accuracy model, we have to find some good way to get best parameters. In our project, we used grid search CV package to find the best parameters. Let's take a look at the code. First, we use the logistic regression package from sklearn to construct the model. Then we put all the possible parameters into the variable params and pass it into grid search CV. And then you will find the best parameters for our model and construct a model. And then we will train the model with our data, and after that we will calculate the accuracy and the AUC. Let's take a look at the results. First, let's take a look at the model we trained by using original data. The original data is the data that have not been pre-processed. We found that the AUC and the accuracy is actually very satisfactory, which means the logistic regression is very suitable for our data set. Then let's take a look at the model trained by the pre-processed data. We find that the AUC and the accuracy are improved a lot. Before pre-processing, the score or AUC score is 0.88, but after that the score become 0.898. So we can see that the pre-processing in step is very useful, and it can improve the score of our model. Then let's take a look at the curve. This is the curve before pre-processing. This is the curve after pre-processing. Also, we can get some other useful information from the logistic regression. For example, we can see the rank of feature importance. Because we can use coefficients in logistic regression model to rank the importance of features, and the features the rank we got is here. Is sort ascendantly, and the code is in this cell. We just simply used the coefficients to sort all the features. Then we will get some good sorted list, and we can find that some features like CP, which is the chest pain experienced by people, and we can maybe explore the relationships between CP and our target in data visualization. So let's take a look.
The second model we use is decision tree. Why we use decision tree? A decision tree is a flowchart-like structure in which each internal node represents a test on an attribute. It is a way to display an algorithm that only contains conditional control statement. Tree-based method empower predictive model with high accuracy, stability, and ease of the interpretations. And it's unlike a linear models, they map no linear relationship quite well. Another advantage is it can easy to adapt at solving any kinds of the problem at hand in classification or the regression model. The logic of decision tree is when we start from the root node, which contains all the attributes of dataset, and after split the training set into subset node, they make decision in each step, and for its subnode, it contains the same value for its attribute. And this decision tree will repeat the process until find the leaf node in the whole branches of the tree. And the final result will be found. When we use the model, we use several processes to use this decision tree algorithm. First, we use the Gale search CV algorithm to predict the best parameter, which it can give us the highest accuracy outcome. And before to start training the data, we should pre-processing our data set. For example, we have to change the data set. Some data is all numbers, numeral, but actually some of our data set should be category. So we change the number to the category. We create dummy variables and it can create small attribute as some columns. After that, we divide the data into training set and a test set. Then we train the model with decision tree algorithm and observe the result. And the result will predict the heart disease. We compare the result before data processing and after data processing. And we find some very interesting result. First, every time we run the model, the accuracy is always changed. It shows that the model is unstable. And we also find the data processing model, the data processing have the lower accuracy score than without data processing. It is unexpected. Why? I think there has some possible reasons. First is overfitting. When data pre-processing, it creates dummy variables. It means it creates more attribute, and more attribute means we will create some more noise decisions. It will make create the depth of the tree, the height, and it lowers the AUC accuracy. For unstable reasons, I think the data set only 300 sites. This is not large enough to make the stable result for decision tree. So we need to improve. One possible solution is use advanced model random forest. Compare the decision tree, random forest have its advantage. First, decision tree is a greedy model. He creates the most optimal decision at each step, but it is greedy. It's not the globally decision. Compare that, the random forest try to optimize the data owned globally. This will make the more accuracy than the single decision tree. And random forest is less prone to overfittings, which is the main problem for decision tree. This is the reason when the decision tree overfittings, because they have like too much attribute and it creates a noise decision. But in the random forest, it can input small sample to each subtree, and it can only make some small sub-random features. And after each subtree make decision, it collect the random forest will collect all the decision and make the final result.
At the data visualization part. In this part, I explored the relationships between features and the target. Let's start from sex. Actually, we found that females actually have higher disease rate in our data set. So in our data set, females are more likely to have heart diseases. As we can see here, this graph is for male and this graph is for female. You can see that female have higher disease rate. Then let's take a look at the age. It's very surprising that younger people are more likely to have heart disease in our data set. As we can see, young people have higher disease rate. And we divide people into two groups. The people the people with age less than 50 was put into the group called young people, and the people with age that's older than 15 will be put into the elders group. Then we can also find some im interesting information from this graph. We find that the average age for the females with heart disease is larger than the average age for the of male that have who have heart diseases. Let's also take a look at the CP, which is the chest pain experienced by people. As if you remember, we find that the CP is a very important feature. So it's very reasonable to see that it can affect the disease rate significantly. If the value is 0, then the person will not, uh, uh, it means the person hasn't experienced chest pain or just have experienced a little bit chest pain. But if the value is 1, 2, 3, then the person has experienced some obvious chest pain. We can see that people who have experienced the chest pain are more likely to have heart diseases in our data set. Also, I think this very reasonable. If we have heart disease, then we are more likely to experience chest pain. Then let's take a look at the feature called the maximum heart rate achieved. We can see that if a person has fast maximum heart rate, then he or she is more likely to have heart diseases. Then let's take a look at the slope. The slope features is means the slope of the peak exercise
From our third and final model, support vector machine. A support vector machine is a discriminative classifier formally defined by a separating hyperplane. In other words, giving label training data, usually, is the supervised learning. The algorithm outputs an optimal hyperplane, which categorizes new examples. We will try linear, Gaussian, and sigmoid kernels in our dataset. Linear kernel seems to be the best one among all three. This means our data is linear separable. A linear separable data also explains why logistic regression is also very effective. Now, let's look at the performance of our SVM. You can see here, before data processing, the accuracy is 0.81, and after the data processing, the accuracy becomes 0.82. Even though the bump of performance is not huge, we can still see a better result. And here is the ROC curve of SVM, which is the after processing data.
Conclusion: this project explores data mining technology to analyze some factors which trigger heart disease. We select 3 models to train the dataset: logistic regression, decision tree, and SVM. Before training, we pre-process the data and compare the results between the before and after data pre-processing. From the accuracy score and the AUC score, logistic regression and SVM are more suitable for our dataset, while decision tree needs more future work to improve its overfitting and unstable, which random forest will do the job.